For over 200 years, Isaac Newton's law of gravity was pretty much the undisputed champion of the cosmos. I mean, it seemed perfect. So how on earth did a young patent clerk named Albert Einstein come along and completely overthrow it? How did we go from thinking of gravity as this force pulling us down to the idea that the very fabric of space-time is bending around us? Okay, let's dive right into this. So right here, this is the core of the whole revolution on one slide. On one side, you got Newton's idea, this invisible, instantaneous force that just acts across the huge emptiness of space. But on the other side, you've got Einstein's totally mind-bending proposal. There is no force at all. It's just objects moving in what they think are straight lines, but through a universe that is fundamentally warped and curved. I mean, these two ideas could not be more different. You know, the real question here isn't just what Einstein figured out, it's how. How can you possibly start with one of the most successful theories in all of science and end up somewhere so completely radical? Well, in this explainer, that's exactly what we're going to do. We're going to retrace his exact steps, one puzzle piece at a time. To really appreciate Einstein's incredible leap, first we have to understand the giant he was challenging. See, Newton's gravity wasn't just some good idea. It was this absolute pillar of science that seemed to explain, well, everything.
Newton didn't just come up with this in a vacuum, of course. He was standing on the shoulders of giants, connecting the dots between Copernicus's sun-centered model, Kepler's elliptical orbits, and Galileo's amazing work on how things fall. For the very first time, one simple law explained both an apple falling from a tree and the moon orbiting the Earth. It was a complete unification of the heavens and the Earth.
And the theory's predictive power was just staggering. It wasn't just descriptive, it made these bold predictions that came true with stunning accuracy. It told us when Halley's Comet would return, and this is the most incredible part. It allowed astronomers to find an entire planet, Neptune, just by calculating some weird wobbles in Uranus's orbit. To question this theory back then, well, it would have seemed absolutely insane.
But then Einstein, back in 1905, published his own revolutionary theory, special relativity, and in doing so, he kind of accidentally created this massive, unavoidable conflict with Newton's perfect universe. And this slide really nails the problem. See, special relativity sets a cosmic speed limit. Nothing can go faster than light, period. But in Newton's model, gravity has no speed limit at all. It's instantaneous. If the sun were to just vanish, poof, its gravitational pull would disappear at that exact same instant, and the Earth would go flying off into space. These two fundamental ideas just cannot both be true. Something had to give. So this conflict, it sent Einstein on this decade-long quest. And it started not with super complex math, but with what he called the happiest thought of his life. Just imagining a person in freefall. This one simple idea began to chip away at the very definition of gravity as a force. Let's walk through this, because it's really cool. When a plane takes off, you feel the seat push into your back, right? You feel that jolt. That's the feeling of being accelerated. It's your body's inertia resisting the change. But when you're falling, like a skydiver, Newton says you're accelerating downwards at 9.8 meters per second squared. So why don't you feel any jolt? You feel completely weightless. What is so different about gravity? Well, the standard answer back then was this very suspicious coincidence. See, every other force, like magnetism, acts on a specific charge. But for gravity, the charge that determines how strongly it pulls on you is your gravitational mass. And by some bizarre coincidence, that's the exact same property as your inertial mass, the thing that determines how much you resist being pushed around. For gravity, and only for gravity, these two totally different concepts are identical. It's weird. So Einstein looked at that and said, maybe this isn't a coincidence at all. He offered a much simpler, if kind of mind-bending explanation. What if the reason you don't feel accelerated when you're falling is because you aren't being accelerated? What if you're just floating inertially, and it's actually the ground that's constantly accelerating upwards, hitting the soles of your feet? This wild idea is known as the Equivalence Principle. Okay, so that's a brilliant and simple idea, right? The feeling of weight isn't a force pulling you down, it's just the ground pushing you up. But this really elegant illusion runs into a major real-world problem: tidal forces. In Newton's world, explaining tides is easy peasy. An asteroid falls towards Earth, but the side closer to the Earth gets pulled just a little bit harder by gravity than the far side.
and that difference in pull stretches the asteroid out. Simple. But in Einstein's new picture, that asteroid is just floating inertially with no forces acting on it whatsoever. So why on earth would it stretch? His new model just couldn't explain it. He was stuck.
And for 5 years, Einstein was totally stuck on this problem. And the solution, when it finally came, was one of the greatest intellectual leaps in human history. He realized he was trying to solve a physics problem when he should have been solving a geometry problem.
This was the masterstroke. He translated the physical problem, how can an object stretch when there are no forces on it, into a purely geometric one. The front of the asteroid and the back of the asteroid are just floating. They are following parallel, straight paths. So his new question was, how is it possible for parallel, straight paths to start to diverge?
Now, to understand his answer, we just need one key term, a geodesic. A geodesic is really just the fancier word for the straightest possible path you can take on any surface. So on a flat piece of paper, it's a ruler straight line, but on the surface of the Earth, it's what we call a great circle route. And this slide right here holds the entire answer. On a flat surface, parallel lines stay parallel forever. That's just basic high school geometry. But on a curved surface, all bets are off. If two people start walking north from the equator on parallel lines, they'll eventually bump into each other at the North Pole. Their straight line paths converge because the surface they're on is curved. And on a different kind of curve, like a saddle shape, parallel lines can actually spread apart. And there it is. That's the solution. The asteroid isn't being stretched by some mysterious force. Its front and its back are both just following their own straight line paths, their own geodesics through spacetime. The fact that those paths diverge, which causes the asteroid to stretch, is direct evidence that the very fabric of spacetime itself is curved. Ultimately, this is the core of his genius. By turning a problem about forces into one about geometry, Einstein revealed that mass doesn't create a force at all. Mass tells spacetime how to curve, and that curvature, in turn, tells all the other matter how to move. This incredible insight became the foundation for general relativity. But it was just the beginning. It took him another 8 years of intense, grueling work to flesh out the full theory. It really makes you wonder, doesn't it? What other hidden geometric truths are just waiting to be discovered about our universe?